When we work with matrices, we use some theorems, some properties of the matrix operations. And addition is very simple. But for multiplication, one very useful theorem holds, namely that the matrix multiplication is associative. That means we want to show the associativity of matrix multiplication. It means that if we have three matrices and we multiply them, then we can do this in two different ways. We can either multiply A times B and then by C, or we can multiply first B times C and then by A, in this order. And the result is the same for any three matrices for which the product makes sense. Well, it is not so obvious, it is not so automatic that every operation is associative. Some operations are, some are not. Say, for real numbers, addition is associative, but subtraction is not. Similarly, multiplication of real numbers is associative, but division is not. A scalar product of two vectors cannot be associative because the result of the scalar product is a scalar, and it is a different to multiply a scalar by a vector than two scalars. Vector product, that we will see later, is not associative. So let us prove this. So on the, first we want to find AB. Perhaps we should write the dimensions of the three matrices. So imagine a matrix A has dimensions A1 times A2. That means A1 is the number of rows and A2 is the number of columns. Imagine B has dimensions B1, B2. And the matrix C will dimensions C1, C2. These six numbers are not arbitrary. There must be some special relation. If we multiply A times B, then we consider this product, this vector with this vector. So A2 must be equal to B1 for this product to make sense. And then this matrix is A1 times B2. The number of columns is the number of columns of this. And when we want to multiply this with the matrix with dimensions C1, C2, then we need B2 being C1. And then the result of the left-hand side will be A1 times C2. And for the expression on the right to make sense, if we write it this way, then BC, for BC to exist, we must have that, okay, let me write it once again. If this is A1, A2, B1, B2, C1, C2, then for BC to make sense, then B2 must be equal to C1. But this is exactly the condition that we have seen already. Then this matrix is of size B1 times C2, and for this product to make sense, A2 must be equal to B1. But this is exactly the condition that we have seen here. A2 is B1. And then the final result will have dimensions A1 times C2, which is as before. So just considering the sizes of the two matrices, of the matrices, it's okay. But what about the results? On the left, first we have AB, and this is a matrix with elements ij being sum of A, I, K, B, K, J, and K runs from 1 to A2. And then we multiply this with C. So on the left, we have a matrix with entry in position I, L being sum of ABIJ, CJL, where J runs from 1 to B2. And now for AB, we use this expression. So we have sum for J running from 1 to B2, sum for K running from 1 to A2, and now we have A, I, K, B, K, J, C, J, L. So this is the IL element on the left. And then on the right we have BC. So we prepare BC. And its KL element will be sum for J running from 1 to B2 of B, L, J, C, J, L. And then on the right, the element IL will be sum of A, I, K, K runs from 1 to A2, times this expression, BCKL, and this is sum for J running from 1 to B2, B, L, J, C, J, L. But we can explain this multiplication. Number times sum is sum of the products, so that means we can swap the sum and the Aij, and we arrive at the same expression as here. Well, up to one small difference. Here we sum over J and then over K, and here we first sum over K and then over J. Does this make any difference? Does this make any difference? It does not. And we can illustrate this by the following simple operation. So we want to show that summing over j and first summing over k of something set jk is the same as if we sum over k after we sum over j. Zjk is some matrix no matter what. But this is the same, because if you consider some matrix, say 2, 3, 5, 9, then if you first sum over columns, then 2 plus 5 is 7, 3 plus 9 is 12, and if you sum this, you get 19. But if you first sum over rows, then you get 2 plus 3 is 5, 5 plus 9 is 14, and this makes the same total, 19. So we can swap the order of summation. That means sum over k, sum over j is the same as sum over j, sum over k. And otherwise the rest is the same. So this proves the associativity of matrix multiplication, which is a very important property. Associativity is very important even in different situations. In cryptocurrency like Bitcoin, this makes the possibility to perform some operation in a reasonable time and to get the result, while it is not possible to find the input, the inverse operation, in a reasonable time. And this is the fundamental property of the mathematical algorithms of current cryptology and cryptocurrency.